So
okay.
I hope you can hear me.
Yeah. So we can hear you well. So let's start our seminar. Today we have another seminar, and our speaker is Stefan S.Suhr from University of Bochum, and he will tell us about the theorem of Lusternik and Schnirelmann for reversible Finsler metrics. The floor is yours, please.
Thank you very much, Roman. Thank you for the invitation to the virtual invitation to Prague, or invitation to virtual Prague. Today I'm talking about something very classical, the theorem of Lusternik-Schnirelmann. Let me state it real quick. Already in the form I want to show you, but I can then discuss what it says. It says that every reversible Finsler metric, you can for the moment also say Riemannian, because that's the classical form. Riemannian two-sphere admits or has at least three simple closed geodesics. So what I mean here, I just mean a S2 with a, let's say for the moment, Riemannian metric. And then we have three curves, gamma 1, gamma 2, gamma 3. These are curves to S2, and they are closed geodesics. Closed geodesics, geodesics, and injective. That I mean with simple closed. So you have a period for your geodesic, and you take the shortest one, and then there are no transversal intersections. So what I mean is, draw your picture. The geodesics I'm talking about look like this, and geodesics that are not allowed, they look like this. This is not allowed.
Excuse me, may we ask a question during your talk, or
of
you
course.
prefer? Yeah. So
yeah,
first, I have to say, in the case of Riemannian geometry, your theorem is classic, right? 100-year-old, something like that.
It's just a two-sphere, yes.
Yeah, but what is the difference? How big is bigger the class of reversible Finsler matrix than Riemannian matrix?
Ah, it's much bigger. It's much bigger. I will give you the definition, then you will see.
Okay,
yeah?
thanks.
Yeah, just for the moment, just stick with the Riemannian picture. Don't worry about the Finsler too much. Just this for the Riemannian, or for Riemannian metrics, the theorem is due to Lusternik and Schnirelmann, and this is in the late 20s, early 30s. The idea to prove this. Then Victor Bangert once wrote that the story of this theorem is very colorful, because the way they get these three geodesics is via a Morse theoretic method, not on the regular loop space, but on a space of embeddings. And if you apply the usual methods of Morse theory to hunt closed geodesics, you have the problem that the space of embeddings is not invariant under these usual deformations like gradient flows or the energy or Birkhoff shortening methods, whatever you want to take there. And there's a long list of authors which try to amend those problems, including them Alexander Taimanov, Werner Ballmann, and Jürgen Joost is also among those. There's a lot of people, and there was never really satisfactory what they delivered as a sort of attempt as the proof. And the idea when we wrote this paper, well, I forgot to mention, this is joint work with Guido de Philippis, Marini, and Marco Mazzucchelli. We set out to actually write down a proper proof, and if you have a proper proof, then you also have it for reversible Finsler metrics from the method I will show you. So this is the Philippis, Marini, Mazzucchelli. So, okay. The theorem is optimal because, remark, optimal, because you have ellipsoids with three rationally independent axes. And they have exactly three closed geodesics. Three simple closed geodesics, sorry. This is, well, you can look this from many different angles, how to prove that. These three closed geodesics, they come about as the intersection of your ellipsoid with the coordinate planes. So basically you have your ellipsoid. And then you have those ones, and which one am I missing? Ah, yeah, of course, this one. Yeah, so the three lines I'm drawing here are the three closed geodesics, and there are no other ones. Because these ellipsoids, they form a certain form of integrable system, and you can show that all other geodesics are not simple closed. There are lots of other closed geodesics, because you know that every two-sphere, Riemannian two-sphere has infinitely many closed geodesics, but all other of them are not simple closed. So maybe remark this here. There are infinitely many. But only three simple closed. Okay. So then this for the Riemannian picture, and of course it applies to the Finsler metrics, because the Finsler metrics are the generalization of Riemannian metrics. And what is actually a Finsler metric, to sort of give you a definition of what I'm talking about? In general, a Riemannian metric is a family of scalar products on each tangent space. And if you have a scalar product, you have a norm. And the Finsler metric is nothing but a smooth, or a norm that depends smoothly on the point. So it's a function from the tangent bundle to the reals, actually to non-positive, but it's not so interesting, not so important. It's a Finsler metric for a general smooth manifold M. Yeah? If you have 3 points, which you will see is a straightforward generalization of Riemannian metrics. If you restricted the Finsler metric outside of the zero section, it is a smooth function. Here is the zero section in your tangent bundle. B, F is actually, like I said, is a norm. It's positive homogeneous of degree 1. That means, so basically F of lambda V is lambda times F of V for lambda positive. And last but not least, it needs to be convex in order to try, satisfy the triangle inequality. And in this space here, this is formulated as the second fiber derivative of the square is positive definite. Yeah? The second fiber derivative of f itself cannot be positive definite because it's degree homogeneous of degree 1, so that vanishes. But if you square it, it becomes positive homogeneous of degree 2, then you have a chance to be positive definite. And this means here for all V in tangent space outside of the zero section. Okay, that's a Finsler metric. Give you, and F is reversible if f of minus v is nothing but f of v. So basically, the integratrix of your norm, your tangent space, there's a symmetric body. Yes? Symmetrically strictly convex body. That's what it says, that the positive definiteness. Yeah? Examples, real quick, give you an idea what we're talking about. Of course, the zeroth example is the norm of a Riemannian metric. Second, what you can do, and this is an important example which I come to in a minute, is if you take the norm of a Riemannian metric and just add some one form to it, where so alpha is a one form on M, on your arbitrary manifold. In order for this to be a Finsler metric, you need that the dual norm of this one form is smaller than 1. Else, this function will not be positive, and then you are in trouble. And if you want something that is not a bit further away from Riemannian world, but not so important to us, is you can take, for example, p-norms. Your classical p-norms, you know, from functional analysis. In Rn, you can, of course, generalize that to, I don't know, parallelizable manifolds if you want. Here, p is some number bigger than 1, and v is nothing but the tuple v1 to vn in Rn. This is also a Finsler metric. It's actually reversible. So let me say that. This is reversible. This is, of course, reversible because it's a scalar product. This is in general not reversible. It's only reversible if alpha is constant to 0. Yeah, if we are in our classical case of a Riemannian metric. So, okay, so this is the scope that we are looking at. And the idea was always that when you have that the proof that should give you the Riemannian version of the theorem of Lusternik and Schnirelmann, yeah, should also give you the reversible Finsler version, just by that the methods you should employ there, these more theoretic methods to make them work, they should also work in the reversible Finsler case. And I will tell you in a minute why we need the reversibility. But before that, let me tell you one quick consequence that is always mentioned in connection with the theorem of Lusternik and Schnirelmann. It's the theorem of Franks, Bangert, and Hingston. It says every Riemannian, and then also, since the theorem is true for the reversible Finsler case, every reversible Finsler two-sphere has infinitely many closed geodesics. So you have to make a difference here between simple closed and closed. But if you're just asking about the classical question of Poincaré for closed geodesics, you will find on every two-sphere infinitely many. Of course, for surfaces of higher genus, this was already answered by Hadamard at the very beginning of the study of closed geodesics, because you have infinitely many prime homotopy classes, and every one of those prime every homotopy class has a closed geodesic. So you get infinitely many of them, geometrically distinct. But the argument doesn't work for the two-sphere. And it's, of course, the argument by Hopf showing that every two-sphere has a closed geodesic, of course, kicked off Morse theory. And then the question was, is it enough to have an infinitely many? And all the methods up to that were ever developed for Morse theory in general don't give you that for the two-sphere, just because the topology of the loop space of the two-sphere is not rich enough. It's too meager. And it's expected sort of that the geodesics that you get there might not be what most theorists call homologically visible. So side comment to higher dimensions, it's completely open, existence of closed geodesics in general. There is a theorem of Rademacher that says for, let's say, at least C3 generic Riemannian metrics, you have infinitely many closed geodesics. There's a claim by Klingberg in his book on closed geodesics, where the proof is false or has a gap, and nobody knows how to fix it. So in general, the question is completely known except for the surface case. Okay, now let me remark on the reversibility. Actually, for non-reversible Finsler metrics, the theorem of Lusternik and Schnirelmann is false, as is also this theorem of Bangert, Franks, and Hingston. The so-called Katok examples, very classical examples from the 70s, they are super simple. You have a two-sphere of constant curvature, let's say of constant curvature 1. And then you have, of course, on the two-sphere, you have the geographic coordinates. Let's call them phi and theta. Let me make you a drawing that we are on the same page. You have this two-sphere. Then my phi is the coordinate of the equator, and the geographic height is the theta. Okay, so this is what I mean. And then you look at the following Finsler metric. You just take your norm of your Riemannian metric of constant curvature 1 and add to it the differential of phi with some parameter epsilon. And this thing, this Finsler metric, this is non-reversible Finsler, like I said before, with exactly two closed geodesics, simple or not, doesn't matter. If, actually it's an if and only if, the epsilon over 2 pi is not a rational number. So the epsilon and 2 pi are rationally independent. This is, as Werner Ballmann in this paper, The Geometry of the Katok example, explained, this is sort of an incarnation of a Reb flow on a certain ellipsoid in 3 dimensions. Yeah, and there you have exactly this picture that you get only 2 closed Reb orbits. You can see this here actually directly from the geometry. So the closed geodesics you get are actually the equator in one direction and the equator in the other direction. They are here counted differently because it's a non-reversible Finsler metric, so they have different length. And all other geodesics are twisted great circles. So what happens under the influence of this term here is that you start out with a geodesic as you would on the round sphere, and this sort of wind misdirects your travel along your great circle. And this has the effect that when you try to come back with your great circle, you don't come back to yourself as you would in the unperturbed metric, but with a little twist. And this little twist is irrational if this is condition here is satisfied. Okay, so actually, if this number here is a rational number, all geodesics are closed, but only the equator ones are simple closed. Okay. Please interrupt me if you have any questions or I'm unclear. Yeah. So what did I wanted to say? Yeah. There is, of course, I should change back to black. Closed geodesics and Finsler metrics were considered, and the theorem of Hopf also shows you by the simple Moss theory argument that every Finsler two-sphere has a closed geodesic. And then it took until 2008 when Bangert and Long proved that every Finsler metric or every Finsler two-sphere, irrespective of reversibility or not, has two closed geodesics. And the method here of proof is a tour de force through the symplectic group. From a geometric point of view, that was not very satisfactory, but it was known already since the 90s that by Hofer and Sender, HWZ in, I think, 93 is the paper, that they know you have generically two or infinitely many closed geodesics for every Finsler two-sphere. Their theorem is more general, but to our situation, it applies in this way: closed geodesics. But the crux here was the genericity. And there has been a recent claim by a group of authors. Christopher Gardner, Honiewicz, and Hutchings and Lin, that true without genericity. So it's always true, they claim, that you have two or infinitely many closed geodesics. So then you could view this now from this point of view, saying, okay, if I have a reversible Finsler metric, I only need to prove that there are more than two closed geodesics, then automatically infinitely many. Yeah? You can view it in this way. So this theorem of Bangert-Hingston here becomes corollary of this more general result in contact geometry together with the theorem of Lusternik and Schnirelmann. Oh, sorry. Is there a question? Okay.
I asked a question about the genericity. Maybe genericity is coming from assumption in Hamiltonian or contact geometry on some, how to say, because I only assume the flow homology or something like that, or I don't know why you need genericity and then you can drop the genericity.
The genericity is there to ensure that stable and unstable manifolds of a certain flow intersect
transversality in symplectic geometry, right? Because you
yes.
like Lagrangian transformation and you go to Hamiltonian setting, right?
Yeah, exactly. No. This part here, it does not talk about two spheres. It talks about rape flows on three spheres.
I see.
Yeah.
So you can draw the genericity. So that means that you use the Lusternik and Schnirelmann theory, or?
No, I think it has nothing to do with that. But to be honest, I'm not an expert here in these
okay.
things. Yeah. So no, I would not. No, I cannot really answer this. Yeah. So what I should have maybe said here is that the unit tension bundle of the two sphere is RP3. So this is nothing but the three sphere modulo Z2 action. So that's where the connection with the rep flows on S3 come from. Yeah. Okay. So what's actually the idea? I talked about that as sort of the very classical idea of proof. Very classical Morse theory, not quite though, but let me put it this way. The motto is Morse theory on the space of embeddings. Since we want simple closed smooth curves from S1 to S2, and we need to add the constant curves for technical reasons, yeah, inside the smooth maps from S1 to S2. Of course, this is a horrible space, yeah, so, as it's written here. The problem is that with this approach, and this plagued all ideas so far, the naive shortening methods create, or might create, it's not really clear if it happens, might create self-intersections. And maybe put it this way. If the following situation can happen. You have a piece of your closed geodesic, or a piece of your geodesic polygon, if you take the very simple Birkhoff process, and you have, it's embedded. That's one piece, then it goes on, and there's another piece that looks like this. So they're very close together, and this goes on and they close to a simple closed curve, let's say. Now, if you start applying Birkhoff very naively, you would take the midpoint of this point and this point and just draw the geodesic between them. Then you see that you get a self-intersection. So such a process, as we know how to, the textbook version of looking for closed geodesics, will not work. Okay, so what we need here is two things. We need a deformation, which comes down to analysis. And when we do Morse theory, we need enough topology. And topology. So let me maybe say something about the analysis first. This is an idea that goes back to Grayson and curvature flow. We look at a certain horrible space, which I call lambda star, which is the space of embeddings of S1 into S2, together with the constant curves, and I divide by the diffeomorphisms of S1. So basically by the reparameterizations of curves. They act as reparameterizations here. Okay, and I have an obvious functional on this space, which is nothing but I take such a class and send it to the length of the curve associated with this class. And of course, it's well defined on this quotient space, because we know that the length is invariant under reparameterizations. Okay, you can look at the Euler-Lagrange equation of this thing. In a very naive way, by taking just directional derivatives and just ignoring all the problems. We don't have so many problems since we're on the space of embeddings, and the point curves is not so interesting for the particular analysis problem I'm looking at. It's nothing but the differential of the length functional, which is take the base point of your Finsler metric, the Finsler metric derivative with respect to the base point minus d ds of the first fiber derivative of your Finsler metric. Yeah. And this closed geodesics will satisfy this equal to 0, as you know. And the critical points on this space, so basically where the differential vanishes, is exactly simple closed geodesics. They are geodesics, they are closed, and they are simple closed since there are embeddings automatically. Since if I have a critical point, it must be an embedding. So maybe side remark, if you do this for a Riemannian metric, you just get the geodesic curvature. The usual defining equation for geodesics is the Euler-Lagrange equation of the energy. If you do the length, you get an additional term, which you don't see really for regular curves, but formally from the analysis side, it has to appear. So then what is Morse theory? It's nothing but the gradient flow of such a function. So the gradient flow on this space, I call this psi t, is nothing but you take a family of curves, differential with respect to the parameter, plus your Euler-Lagrange equation, your differential of the length at this curve equal to 0. And this is the baby example of a curvature flow. So that goes back to Grayson, then Angenand, and Oakes. They studied this as a curvature flow. This is called the curve shortening flow, because it's actually the negative gradient flow. Yeah, shortening flow of this Finsler metric. They looked only at the Grayson and Angenand only looked at the Riemannian picture. Oakes then generalized this to also Finsler metrics. The problem here is, as a curvature flow, because these things are parameterization invariant, it is actually degenerate parabolic. And in order to have a good flow, you need to get rid of the degenericity. Yeah? This is a degenerate parabolic equation. But is parabolic after gauge fixing. This is if you know a thing or two about Ricci flow, there it's called the Turk trick. So what you do is you simply take your embedding in which you want to start your flow, and you write every neighboring curve as a graph over your curve with respect to where the function of is given by in which direction you go in the unit normal direction. Yeah? So any neighboring curve would look like this. And then if you do this, you get really a parabolic equation. Then you look into your PDE literature. So neighboring curves as graphs. I wanted to say that. Then you look in your PDE literature, and then you see that these sort of things, they have a smooth flow, which actually depends in the C infinity topology smooth continuously on the initial value. Then you will say, all good and fine, I have my flow, solution of this parabolic equation. Does this preserve embeddedness? Yes, it does. And that's nothing but the maximum principle for the parabolic equations. Preserves So, and then, so let me maybe give you a bit of history here additionally. Grayson wrote in his first paper on this curve shortening flow, then this should imply that, or his flow there implies Lusternik Schnirelmann, but he wrote this in a paragraph saying, yeah, this equation should, or a certain estimate should do it, but he never gave any details. And people in Riemannian geometry were always saying, yeah, they're all good and fine, what Grayson writes there, but we want to see detailed proof. And that was the starting point for my work with my co-authors, that we actually sat down to prove the following theorem. Let L be positive and epsilon, a smaller number, also positive, be given. Then there exists delta positive and a function tau, which is defined on the space of embeddings of S1 into S2 with length less than L plus delta. This is a continuous function, you don't need more than that, to the positive real numbers, because it's supposed to give you a certain parameter time for your flow, such that the following holds. The curvature flow with initial point gamma at t is in a certain neighborhood, which we call UL epsilon of the critical points, unit the embeddings from S1 to S2 with length less than L minus delta, if the t is bigger or equal than tau of gamma. So here, let me give you the definition of what we call UL epsilon. Is nothing but a certain neighborhood of the set of simple closed geodesics, those gamma, such that L gamma is in the interval L minus epsilon, L plus epsilon squared, and the maximum of the geodesic curvature of gamma is smaller than epsilon. It's the geodesic curvature. Maybe in a more, if you know Morse theory, what does this mean? You have a certain critical level, L, where you have a certain critical point. And if you want to, so outside your negative Morse flow looks like this, except at this point. Yeah. And you want to push a certain level of your functional, this functional here above, you want to push it down below this level. Of course, you cannot do that. You cannot push with your gradient flow past this critical point. But what you can do is you can push it like this. So this is the, and then you know that you are outside of a certain neighborhood of your critical point, you are below the critical level. In finite dimensional Morse theory, this is an exercise, yeah, for example, in Milner's book on Morse theory. In these infinite dimensional Morse theory settings, this is an actual question. You have to prove this. It's not so obvious. It's not an exercise how to do this. It's there really goes iterative estimates on the parabolic equation, iterative a priori estimates on this parabolic equation. Enter the proof. Okay, how much time here? So with this, you can, if you have a sufficiently much topology, you can prove that there are, for all the topology you have in the space of embeddings, modulo the diffeomorphisms, you have a closed geodesic because there are sufficiently many critical points. Yeah, you just take a homology class representing your non-trivial homology. Start the gradient flow here, this parabolic flow, and then this thing will converge to a closed geodesic. So I can view it, formulate it like this. So if the embeddings from S1 to S2 modulo the diffeomorphisms, we don't need the point curves here right now, has sufficient topology, there exists existence of closed geodesics, of simple closed geodesics. For the simple reason that your gradient flow will converge to these critical points. Okay, so the question is, do we have enough topology? And this is actually much more classical subject than the analysis, because that was actually what Lusternik and Schnirelmann got straight on first attempt. That you have the following. Let me maybe say this a bit. Okay, yeah. Let me put this way. So how do we do this? Start with a drawing. So we take the round two-sphere, and there we have all the great circles and all the circles which are parallel to them, which are of course not great circles, but smaller circles. So, and we can parameterize these great circles here by the following, by the orthogonal direction, which here in this case would be this point, plus the level at which they are, this point x, and this is lambda x, at which level the orthogonal complement intersects the sphere. Okay. So how do I put this mathematically? I define a certain bundle. This is nothing but a certain class of points in RP2 plus multiples of that point in RP2. This is an element of RP2 times the 3-ball, where x is actually a point on the sphere and lambda is some point between -1 and 1. If you want, this is the unit ball bundle, whereas the ball here is one-dimensional, in the tautological bundle over RP2. If you take the tautological bundle and then only the vectors in there with length at most 1, then you get exactly this object. So, and if you sort of stare at this long enough, or you know enough about topology, then you will see that the cohomology of this thing with Z2 coefficients, this only works in Z2, all this picture here, is generated by one element, omega, and breaks off, of course, at level 3. Yeah? Here, omega is a generator of the first homology, which is actually, yeah. So, okay, and we want to use this space with its topology to get enough topology in the space of embeddings. So we need to embed this thing into the space of embeddings, and this embedding I call iota. With respect to the boundary, because this is important for the topology, into this lambda, lambda 0, we call this. And the boundary is sent to the constant curves, because the boundary is nothing but where these curves here generate to the green point. Yeah, this is the boundary here. It's one boundary point. What do I do? I just send how do I say this? I send such a class X lambda X to the intersection of S2 with X plus X orthogonal plus lambda X. Yeah? This is exactly the blue line I drew there. Okay, so and the dilemma is here that the induced map on the fundamental group is injective into the fundamental group of lambda 0. This is lambda 0 is the space of embeddings without the point curves, and it implies actually that the induced map on the first homology with C2 coefficients is also injective into this first thing. So you basically, this piece of tautological bundle generates, or you will see, generates the topology of the space of embeddings. And maybe, yeah, since I'm running a bit out of time, let me maybe say, just verbally, I said all this will entail that this iota star, or the induced map iota, is actually an injective in the entire homology. So all these classes here will survive when mapping them into lambda 0 relative to the boundary. So what you get is, after a lot of discussion, is 3 subordinated Z2 homology classes H1 bar, H2 bar, H3 bar in this space lambda star modulo the these are relative classes modulo the boundary, the point curves, constant curves, which then entails you get 3 critical values which are ordered like this. So then you can make 3 cases. If they are all different, you have 3 simple closed geodesics. Because to each critical value belongs a critical point, which is a closed geodesic, and it cannot be an iterate of another because they're simply closed. Second case, if L1 is equal to L2 or L2 is equal to L3, then every point in S2 lies on a simple closed geodesic. which then, of course, obviously implies that there are infinitely many simple closed geodesics. And the third case, which was also a bit overlooked before, that not overlooked, but the consequences of it were sort of not really discussed. If all three values coincide, then you actually have a Finsler reversible Finsler sphere, which all of whose geodesics are simple closed. And this is what's called simple Zoll. And Zoll metric is a metric, a Riemannian metric, or Finsler metric for that matter, such that all geodesics are closed and have the same length. And simple then means they don't have any self-intersections.
So your or in the second case is more or less like an alternating or, because otherwise third case is a part of the second case.
Yes, yes. Yeah, of course. I mean, in the third case, if you have simple Zoll, then every point automatically lies on a simple closed geodesic because every geodesic is simple closed. Yeah. But in the second case, if only two critical values coincide, not necessarily all geodesics are closed. And maybe come to, let me see, what can I say? Last few minutes. The third case was actually not really contained in the literature. There was a separate paper I wrote with Marco Mazzucchelli where we proved this for the Riemannian case. It was sort of noted for positive curvature by Beimann, Thorbergson, and Ziller on the early 80s already, but they were limited to positive sectional curvature because they were using the Birkhoff map to get the result. This last case here also has an analog in higher dimensions, which I proved with Marco Mazzucchelli, without the simple, of course, where you need that a certain set of critical values in the loop space coincide. It's a more classical more theoretic picture there. And maybe one last thing I can mention as a consequence here is the following theorem, which for the Riemannian case is due to Grommel and Grove, and is actually proved by Frauenfelder, Lange, and myself for the reversible Finsler case. And it says that if you have a two-sphere with a reversible Finsler manifold, such that all geodesics are closed, then they cannot have self-intersections because they are simple closed. As you would expect, yeah, if you look at the constant curvature two-sphere, all geodesics are closed, but they don't have self-intersections. Here, remark, which I'm just say maybe in words, there is a standing conjecture by Berger that says this statement should be true for Riemannian metrics on all spheres. It's been proven for Riemannian spheres of dimension at least 4 by Radetzky and Wilking, maybe 6-7 years ago. S3 is still open, oddly enough. And the last thing for the projective space, if you look at RP2 and you ask yourself, you have a Riemannian metric on RP2, all of whose geodesics are closed, what happens then? And this is an old theorem by Green, which then in the full generality was proven by Pries, maybe 15 years ago, that if you have a Riemannian metric on RP2, all of whose geodesics are closed, then it's already the standard metric. So it's constant curvature. And there is actually this rigidity, which becomes very flexible when you have Finsler metrics. And there is a paper by S.Suhr, I think is his name, who proves that at least the space of Finsler metrics, which are Zoll on RP2, is contractible. So that's a very interesting paper that probably needs a bit more looking at in order to understand all these consequences. Okay, thank you very much. That was all I wanted to say for today. And I'm open for questions.
Thanks a lot for the talk, Stefan. Are there any questions, comments, remarks?
So I would ask you, so the main problem, you do most theory on the space of the embedding of the, yeah.
Yes.
So what is, how to say, so you compute the non-trivial cohomology class or what?
Yes, I mean, mostly what does it do? It says, okay, we have a space that has topology, so every function has to have so and so many critical points. Exactly. Here, what you first need is the topology. And then you need to verify that that the topology sort of, yeah, in finite dimensional Morse theory on compact spaces, or let's say Morse theory on compact spaces, then you automatically know that there's a critical point. But in the absence of something like Palais-Mail condition.
So you use Palais-Mail condition.
Yeah, exactly. Things might run off to infinity and you lose, even though there's topology, you don't have critical points.
Yes.
Because they sit at infinities. Yeah. So you need. Yeah.
So yeah, so use so that's the question. That means that if you try to extend the horizon, so what which direction is easier? That's more how to high dimensional sphere or drop the condition of Finsler metric.
Well, this curve shortening flow is something purely two-dimensional. It does not work in, well, you can write something down in higher dimensions, but basically all the properties go, because you're looking at a curvature flow with higher codimensions, and people have been dancing around this for a long time without getting really somewhere. Yeah? So this is something purely two-dimensional, and it's actually in a certain way the end of the story for this particular problem. So I don't think there is much more to do in two dimensions in terms of existence of closed geodesics. What of course is widely open is understanding a space of Zoll metrics on S2, for example. Then nobody really has a clue what that space looks like. So that's a very interesting problem. And of course, construct an example of a Zoll metric, not on the sphere, of higher dimensions, which is not simple Zoll, or which is not simple Zoll, for example. All these things are not really known. No, actually, yes. Maybe I stated it a bit wrong what Hradecki and Wilking proved. They said if you have a sphere, all of whose geodesics are closed, then they all have the same length. But nobody knows if they are simple or not. And nobody has actually, so far, I don't know any attempt or an example that would show that you have geodesics which can self-intersect some of them and some of them don't, or how often. And yeah. Because in higher codimensions, you have to, in two dimensions, they cannot intersect, but in higher dimensions, they can do like basically like this. You know, they can move through each other. There's no which.
So in high dimensions, there is no like even expected results. So it's not really clear what to expect.
Not that I know of, no. I mean, really, it's a lack of fantasy.
Yeah, right. Yeah.
I mean, by the usual principle, it should exist, but because it's not strictly forbidden should exist. Yeah. So.
Yeah.
I don't think anybody has an idea how to construct a concrete example.
So you
Because
think
of
the condition on the reversibility of Finsler metric is only this wicked condition, right? Because the only condition you put on the Finsler metric is a reversibility, right?
Yes, yeah.
So that is only wicked condition. You cannot how to say make it weaker or another condition.
No, because of this Katok example, basically. Yeah?
I see.
This is you see these Katok examples. If you send the epsilon to 0, they converge to the round metric. So it's not even that this sort of isolated away from the Riemannian metrics or something like that. You know? This phenomenon.
So that's only the end of story, you say?
Yeah, sort of in a certain way. I mean, if somebody comes up with a good condition, which non-reversible Finsler metrics should satisfy the theorem of Lusternik and Schnirelmann, then that would be great progress. But again, I have no clue what that should look like.
Right. Any other questions or comments? If not, then let's thank the speaker. And